Objectives of today's class are the application of conservation of linear momentum and angular momentum for a rigid body. So the linear momentum is denoted by L, and that's mass times the velocity of center of mass. And when there are no external forces acting on the object, or the forces are internal to the system, the linear momentum is conserved. So L1 is equal to L2. Okay. The other quantity is the angular momentum. It's denoted by M, and it's always about a point. So MO is IO omega. Well, not a point, but rather an axis. In 2D, it looks like a point, right? And if the external forces are zero, or the external moments are zero, or the moments are internal to the system, then we can write MO1 is MO2. So normally M is a vector. It has three components, x, y, and z. But since we are only looking at planar bodies, the angular momentum is always pointing in the k direction. So it's a scalar for us. But that's not true for 3D bodies. Only true for two-dimensional objects. So that's it. So method of analysis. One, draw FBD and coordinate frame. The second point is apply conservation of momentum. And here you got to be you got to think about which formula you want to apply. Okay. When you have a rigid body and there are reaction forces, those reaction forces usually show up in the L equation, but they don't show up in the M equation if you take the angular momentum about appropriate points. So usually the M equation is more useful if you don't want to find the reaction forces, but you're only interested in things like angular speed. And then the last part, and this is optional, it really depends on the problem, use kinematic equations. To solve for position or angle. Okay. So by default, conservation of momentum will give you either the linear speed, because what's the conservation of momentum? It's L, which depends on v, and M, which depends on omega. So it gives you speeds, either the angular speeds or linear speeds, and from that you can use kinematics to figure out position or velocity. So typically pulley problems. Okay, with that, let's start solving problems. Okay, so the 80 kg man is holding two dumbbells while standing on a turntable of negligible mass. So this is a turntable. which turns freely about a vertical axis. When his arms are fully extended, okay, it's shown right here. the turntable is rotating with an angular velocity of 0.5 revolutions per second. So let's say omega 1 is 5 revolutions per second. Determine the angular velocity of the man when he retracts his arms to the position shown. So this is position 1, this is position 2. You got to find the angular speed when his arms are at 2. When his arms are fully extended, approximate each arm as a uniform 6 kg rod having a length of 650 mm and his body as a 68 kg solid cylinder of 400 mm diameter. So when he is in position 1, what this means is his body is 68 kg solid cylinder. So that's the man's body. It's 68 kg cylinder with 0.4 meter diameter. Each arm has a uniform 6 kg rod. So I believe that's how it is. Okay, this is 6 kg and length of 0.65. Okay, I'm just going by this. It looks like this distance is 0.2. What else? He also holding a dumbbell in a hand. So that's the dumbbell, which is so it's each of those blocks in the dumbbell is 5 kilograms. So the dumbbell is 10 kilograms. The weight of his arm is 6 kilograms and his body is 68 kilograms. So I'm really drawing his left hand, okay, but we'll basically use that to find inertia later on. Okay, so that's part 1. With his arms in the retracted position, okay, let's draw that. The man has an 80 assume the man has an 80 kg solid cylinder of 0.45 mm diameter. So the same figure now, but this thing is 80 kgs and the diameter is 0.45 meters. Each dumbbell okay, so that's about it. So 80 kgs includes his mass as well as the mass of his arms, and it's also shown here that when it's retracted, the dumbbells are 0.3 meters away from his axis of his body. So this is 0.3 meters and that's 10 kilograms. Okay, so essentially what's happening is he's on a turntable. This, by the way, is a turntable, right? He's spinning at an angular speed of 5 revolutions per second. When he's spinning, what he does is he holds 2 dumbbells as shown, and then he quickly moves them like this, and then you're asked to find the new speed of the turntable. Okay, so the forces, if you consider the person, are all internal to the system. So this is a place where you can apply conservation of angular momentum, okay, not the linear momentum, because if you apply linear momentum, there's going to be a force between the turntable and the man, which will show up in your equations, and you don't want that. So you want to do conservation of angular momentum about the vertical axis. So we can write I1 omega 1 is I. So before I write that, let's apply conservation of angular momentum. Okay, which states that I, let's call this axis O. Okay, so IO1 omega 1 equals IO2 omega 2. Okay, we know what omega 1 is, we do not know what omega 2 is. We got to find IO1 and IO2, and that information comes from these two figures I drew on the right side. Okay, let's find IO1. Okay, so for IO1, we have, well, 5 pieces there. His body, his 2 arms, that's 3, and the dumbbells. Okay, but really we have to find the inertia of 3 things: his body, 1 arm, so we can do twice that arm, and the dumbbell, and we can do twice the dumbbell for the inertia. So let's start with the body. So 68 kgs. So I'm going to write the formula and then sub in. So mass body, we got to know what's the inertia of a cylinder about an axis passing through the center. It's not along this axis. Okay, along this axis, the inertia is the same as that of a disk. It's half m body d body. Sorry, let me write r body. Okay, this comes from previous chapter, remember? And if in the exam I'll give this to you. Don't worry about it. Okay, let's write the inertia of the arm. Okay, now when there's a cylinder this way, you want to find the inertia about an axis passing through the length of the cylinder. That inertia is 1/12 m times length squared, right? So that's half m arm length arm squared. So this is the inertia about this axis. Sorry, 1/12, my bad. Okay, so it's about this axis, an axis passing through the center of mass of the cylinder. We assume it's a uniformly distributed mass, so the center of mass passes through the center, the geometric center. But we do not want the inertia about the center of the cylinder, but we want it about an axis passing through O, right? This is O. So we got to use the parallel axis theorem. So parallel axis theorem says that the inertia is inertia about the central axis plus mass times the distance between the axis, which we are interested in, O, to the distance of the center of that object. So it's this axis. So we got to find the distance from this axis to this axis. Okay, so you can see that's 0.2 plus half of 0.65. So 0.2 plus half of 0.65 is 0.525. So I'll write 0.525 square. And since this is just 1 arm, I'm going to multiply this whole thing by 2, because we have to do the same thing on the other side, this other arm. Okay, but we're not done yet. We just finished with 2 things. We have to still find the inertia of the dumbbell. So that's going to be, now the dumbbell is assumed to be a point mass. That is, it's not, you're not given the diameter of the dumbbell or anything like that. So it's a point mass. So when it's a point mass, the inertia of a point mass is always mass times the distance from the axis squared. So the mass of the dumbbell, I'll write it dB, times the distance. This is the distance from here all the way to the center. So that's going to be 0.65 plus 0.2, so 0.85. And since there are 2 of those, that's going to be twice. So M body is 68, R body is 0.2, M arm is 6, L arm is 0.65, MdB is 10 kilogram, because there are 2 of those clocks in out. So if you put all those numbers in, you get IO1 equals 19.54 kg meter square. Okay. Okay, so that's one part. So the other part is finding I2 or IO2. So IO2 is, we're going to look at this figure now. Okay, so again, the man is, and his arms are approximated as a 80 kg cylinder, and the axes are right along the vertical. Okay, when you have that scenario, the inertia is m body times r body square divided by 2. It's the same as that of a disk, because if you look at it in a way, along this axis, it's like a disk, right? Plus there's a dumbbell at 0.3 meters, and that's a point mass, so mdb times 0.3 square, because the distance between the dumbbell and the vertical axis is 0.3, and since there are two of those, you've got to put a 2. So in here we got to put m body is 80 kilograms. It's not 68. R body is half of 0.45. It's 225 meters. So it's not the same as over here. So IO2 comes out to be, I get 3.825. So IO1 times omega 1 is 19.54 times it's 0.5 revolutions. Now we can convert to radians and back to revolutions, but I just keep it in revolutions. It won't change anything. So I'm going to keep it as revolutions per second equals 3.825 times nu omega 2, where omega 2 is in revolutions per second. I did not convert it. So that comes out to be 2.55. Okay, so what's very interesting is that the guy is spinning at 0.5 when his hands are like this, and when he does this, what he's effectively doing is he's reducing his rigid inertia, right? The inertia was 19, and now it decreased to 3.8, and the effect was the angular speed increased, so it's spinning faster. Okay, do you think something like this is physically possible?
What I'm going to do is I'm going to stand on that platform. I'm going to hold these weights out. When I hold these weights out like this, I'm going to spin like this. When I hold them out far, do I have a lot of rotation inertia or a little? How about when I pull them in? A little? So if I get here rotating like this, and I hold them out, what happens when I pull them in? Ooh. Easier to rotate, gang. Harder to rotate. Easier to rotate. Harder. Woo! Woo! Okay. You see such thing? All right? All right? You go to the you go to the ice ballers, you see the skaters turning around like that, they're spinning, 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 and when they're spinning, they pull in like this, yeah? Go fast, 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 and then they come on. Da-da-da-da! People think they're going like that for applause. You know what they're doing? They're trying to save them from breaking their necks. You increase your rotation. Isn't that neat?
Okay, so the 2 kg rod ACB, this is 2 kilogram rod ACB, supports 4 kg discs at its ends. If both discs are given a clockwise angular speed of 5 radians per second, while the rod is held stationary, so the initial angular velocity of the rod is 0. Determine the angular velocity of the rod after both discs have stopped spinning relative to the rod. due to frictional resistance at the pin A and B. Okay. Motion is in the horizontal plane. Neglect friction at pin C. Okay, so initially these disks A and B are moving with a angular speed, and the rod is stationary, it doesn't move. Okay? And by the way, this setup is in the horizontal plane, so it's moving like this. It's not this way. And then what happens when you let it go, because of the coupling, because this disks are spinning, it tends to sort of entrench the rod, and the whole system moves with the same angular speed. So when the problem says there's no relative speed between between the disks and the rod ABC, it means that the whole system is moving with a single angular speed. The whole thing has a single angular speed. Okay, so what you got to do is, well, the initial speed and the final speed are related through the conservation of angular momentum, and you can do that because there is no external force. If you consider the system as a whole, then the forces which make the whole system move with a uniform speed is all internal to the system. So I'm going to use conservation of angular momentum. So H about C1 is equal to H about C2. Okay, initial momentum inertia times omega 1 is final the new inertia of the complete system times omega 2. Okay, I'm going to put a summation here just because there are multiple masses. So let's find I1 omega 1. So the rod ABC is stationary, ACB is stationary. It's only the disks which are spinning. The inertia of a disk is half m r square times omega b, let me call it m-a-r-a square. Oh, sorry, looks like it's b and a. So m-b-r-b square omega b1 square. That's about it. So this is the inertia of a disk, the first part, and omega is the angular speed of the disk. Similarly, there's half m-a-r-a square omega a1. Okay, now note that I have not used the parallel axis theorem. I have not found the inertia of this. Inertia is the inertia about B, but it's the same as the inertia at C. That's because B is spinning about its own axis. It doesn't quite rotate about point C. When you have a pendulum, it rotates about point C. You got to find the inertia about the axis which passes through C. But in this case, if the pendulum had a disk which was spinning and the pendulum was stationary, then the inertia of the disk, you don't have to find it about the point C, because that is, you don't have to invoke the parallel axis theorem, because it is not spinning about the point of contact or the hinge point. It's spinning about its own axis. So in such cases, you don't have to use the parallel axis theorem, because it rotates about B and not about C. Okay. So this is so it turns out that the I omega is the same for this. So I could have in fact written is twice of this. So it comes out to be 2 times half times 4. 4 is the weight of the disk, times the radius square. So the radius is 0.15 square times the angular speed, which is 5. Okay, that is Okay, I don't have the answer here, but that's what you should get. And then I 2 omega 2. So now the whole system is moving as a single unit. Okay, and now you got to apply the parallaxis theorem in order to find the inertia of the disk, because the whole thing is moving about an axis passing through C. So 2 times half. I'm only going to write the inertia of A, and then that's simply twice for the other mass, times R A square plus M A times the distance between C and A, which is 0.75 square, right? Times the inertia of the rod ACB, and the inertia is 1/12 mass of rod times the length of rod square. Okay, so this whole thing times the omega, and omega is here an unknown. We don't know what the angular speed is. Okay, so this is 4, RA is 0.15, M rod is 2 kilograms, and the length of rod is 1.5 because it's the complete length, 0.75 times 2. So if you are applying I1 omega 1 equals I2 omega 2, we get omega is 0.0906 radians per second. Okay, so that's the answer. Next class, so I've actually done a class early, if you look at the syllabus. So I'm going to use the next 2 classes to do the review. So next time I'm going to give you a sheet which says how to go about solving problems. In this class I'm going to do a couple of problems, and I think the last class I'll be trying to do mixed problems, so which have concepts from multiple sections. Okay, I'll see you on Wednesday.